Okay, the third one from the upper ones. What is the speed of a periodic wave disturbance that has a frequency of 2.5 hertz and a wavelength of 0.6 meters? Well, the wave equation is V equals lambda F. There's F, there's lambda. All you gotta do is multiply those two values together. So 2.5 times 0.6, whatever that is. Did you do that and not get a value from the bottom? Oh, okay. So that is like the idea there is that it's just like it's one passing of, so a wave does disturb whatever the medium is. So a periodic wave disturbance would be one shot of that packet of energy passing through as a frequency of that and a wavelength of that. Yeah, no, that's all it is. Anything else from anything here anyone want me to look at? Going once, twice, thrice, 6. The bonus-ish one. A periodic longitudinal wave has a frequency of 20 hertz. It travels along a coil spring. If the distance between successive compressions is 0.4, what is the speed of the wave? It's the same as 3, which is why I didn't originally assign it. But this is, I said this was an interesting one because it is what I demonstrated in class. V equals lambda F. They give us the frequency and they give us the wavelength. So the distance between successive compressions is this value, that is the wavelength. So it's just going to be 0.4 times 20, which should be 0.8 meters per second. So basically, that's the reason I said it was interesting is because that's what I did in class. Lena and I did in class. Just demonstrated that. And oh no, that's not 0.8. It's 8 meters per second. 4 times 20 is 80 divided by 10 is 8. Yeah. That's all it is. 2 was an interesting one if you did look at 2. It's just the idea that an echo is there and back. So you either have to have the time or double the distance to get a good understanding of the speed of the hiker's voice. That was it. Okay, so today we're going to look at a bunch of different properties of waves and how they behave. So here we go. Reflections. Reflections are something you're familiar with. The fact that you can see yourself in a mirror means light is reflecting. Light is just a specific kind of wave. So we're going to look at a couple. We're going to look at water waves. We'll talk about water waves, sound waves, and light waves. Because they all do behave roughly the same way. Waves reflect. That energy as it's traveling through a medium, if it hits a barrier, they bounce. You experience this with sound in the form of an echo. You experience it in light in the form of, well, the fact that you can see yourself in a mirror or in any surface is light bouncing back off of, hits you off that surface and then back to your eyes. So this is a property all waves have, and they reflect in very specific ways. Water is one that you're, again, not necessarily going to be super familiar with because we don't live super close to the ocean unless you spend a lot of time at the wave pool as a child and said to yourself, oh, look at the waves as they bounce. Water's the weird one. Waves that hit a barrier will reflect at the same angle at which they approach the barrier. That is just a true statement of fact. Will be reflected at the same angle at which they approach the barrier. There's no change in the speed or wavelength of the incident waves. They just now are moving in another direction. The direction of the incident wave is changed. And so there's some language in here that is new. This language here of incident, that language just means the original incoming wave. Original incoming wave. And so one of the interesting properties of this is that, I mean, if you've ever played pool, it's the same idea there too. It's all a game of angles. And with, like in pool, waves, the angle of incidence is going to be equal to the angle of reflection. And now that angle is always measured off of what we call the normal, and we've talked about normal before. We talked about normal forces, and the whole key with normal forces is that they are always, whatever it is, perpendicular to the surface that the object was touching. And so these angles, the angle of incidence and the angle of reflection, are also measured normal to whatever surface is being bounced off of. So normal means, let's draw a line in here. I'll take it this one. And you want to draw that line as best as you can, perpendicular to the surface. This is my attempt at drawing a normal line. And so the wave here is coming in. This is our wave. The direction of the wave energy, the incident waves, and this angle here is what we call the incident angle. It's the measure of, it's the size of the angle between the normal and the direction the wave is traveling. That's, and we call it theta I, the incident angle. And the way that this diagram is drawn, this angle here is equal to that angle there. Actually, is that true? No, that's not true. This angle there is equal to this angle right here. So if this angle is, if this little piece is 30, this normal is 90, that means that guy there is 60 degrees. So on this thing, the angle here is going to be 60 degrees. If you need more paper, I got a whole box right by your feet. Not printing?
I must have printed to the wrong spot.
Oh, okay, good luck. And so if the wave packet is coming in at 60 degrees, it's going to leave at 60 degrees. So that angle right there is going to be 60 degrees. And so you're going to get, the waves are going to bounce off. The direction isn't going to change, so this distance from here to here is going to be the same as these wave lines that we've drawn here to here. And this angle right here is called the angle of reflection. They're just going to bounce off. So same idea here. I've got waves coming in here. If that's 75 degrees, I'll draw our normal line off of here. It's easiest to turn the page. Put it right there. There's our normal. And so the wave is coming in here, our incident wave. And we want that angle in there. So if this angle here is 75, that means that this angle in here has got to be 15. And this becomes our theta I, our incident angle. And so what this means is the waves, these water waves, are going to hit this wall, and they're going to bounce off at the same angle they came in at. So you're going to get something that looks like this. We've got pink. They're going to bounce in. And they're going to look like something like that. And now there's a property of waves that we haven't talked about yet, but we will. When waves start to interact, we call that interference. And so wherever waves overlap, like these lines overlap each other, you're going to get effects where these waves are going to actually build on each other. So if you spent any time at the wave pool, did anyone go to the wave pool as a kid here in Abbotsford? None of you. Okay, never mind. Take it all back. You would have experienced some of the cool effects of this. Okay, so reflections of waves. Flip the page. Let's talk about reflections of light waves. Light does the same thing. When light is reflected off of a mirror or any surface that light is reflecting off of, you get the same effect. The angle of incidence is equal to the angle of reflection, always. For any wave, and light is a wave. Hey, what's up? You have to leave me your phones. Then you have to leave me another object of value. How valuable is your bracelet? Could I sell your bracelet and buy more calculators if you don't return my calculator? Is that no, like is your bracelet that valuable? Okay, then I'll take it as trade. Right here. Japanese, you need one too? You don't have anything. Where's your phone? Leave me something. No, it's right here. Sorry. Thank you. Give me a shoe. Sure. It'll at least the very least it'll remind me that you have my calculators. Thank you, ladies. Okay, light's the same. Light is an easier one to draw. We just draw light as a straight line. So this angle here is theta I. It comes in, it hits whatever reflective surface we are working on, and it bounces off at the same angle. Theta I and theta R always measured from the normal line, going to be equal to each other. Where things get really interesting is now with light, we actually can start to curve our surfaces, and we get these really neat effects. Because you have to remember, light's not just coming in on one band, right? It's coming in as a whole kind of beam of light. And so what happens is if you have a curved reflective surface like this, an example of this would be like a security mirror in 7-Eleven. You get light coming in from all over the store, it hits this circular mirror, and you're going to get this angle and that angle are going to be equal for all of these things. Theta I equals theta R. You're going to get light bouncing in here. Theta I equals theta R for this interface. Theta I equals theta R. And for every single beam, you're going to have these angles being equal. But for light that was all coming in at the same direction, you can see I hope you can see what's happening here. These angles that it's bouncing off at are getting bigger depending on where the light hits the reflective surface. So when it hit over here, it was a smaller angle than when it hit in the middle, which was still a smaller angle than when it hit on this far curved side. And so what you get here is if the light is bouncing off at different angles, they were all coming in at the same angle. If it's bouncing off at different angles, what's that doing to the image? What would you see if you were standing somewhere else looking at this mirror? So examples of this are a security mirror. But even younger than that, what kind of surface is this? Yeah, here today. Yeah. Okay. It's an interesting thought. Why do you think it would be smaller? Sorry? Okay. There's another effect I'm looking for, not so much size. No, not quite. So a security mirror is an example of this. There's another example of a curved reflective surface that as a child I spent a ton of time playing with, and I'm hoping you guys did too, because if you didn't, you were deprived as a child. It's nothing fancy. Hands up if you had cereal for breakfast as a kid and ever spent any time looking at yourself in the spoon. Yes? Really? And you didn't do this? You were deprived as a child of your own design. This kind of curved surface is the back of a spoon. What do you look like on the back of a spoon? Yeah. You're upside down and you're not on the back of a spoon. On the back of a spoon you're right side up. The front of the spoon you're upside down, which is what we're going to talk about down here. On the back of the spoon you're right side up, but what do you look like? Do I have any spoons? Metal spoons? I do have a metal spoon. It's clean. I was just using it to scoop coffee. Pass it around. Look at yourself. Put your phone away. Look at yourself in the back of that spoon and pass the spoon around. What do you look like? No, Liam, look at yourself. It's a spoon. Yes, look at yourself in the back of a spoon. What happens to you? Yeah, you get stretched. I want all of you to look. I mean, yes, I know it's silly. Look at yourself in the back of the spoon. And wherever it ends up, here today it'll end up with you. Keep the spoon, because I'm going to make you do it with the other side. So on the curved back of the spoon, the fact that the angle is getting larger depending on where the light hits you gives you this kind of stretched image effect. Your nose kind of looks big and right at the center, but the rest of you kind of peels back. Here today you do it too. And then keep the spoon because you're going to do the other side. When you've got something that looks like this, all the light comes in on this kind of reflective surface, and you're going to have light that's going to bounce like this. That's not a great job of making the angles the same. Let's just say that they are. Theta I equals theta R. If it bounces in on the normal line, this is going to bounce off on the normal line. And then this one is going to bounce in like that, where theta R over here is going to equal theta I. And so look what happens. If, for example, with the spoon, let's say I turned this thing sideways, Mr. McDonald. If your face is over here, this is where your face is, the light is going to bounce off your face and it's going to go towards the spoon. This is the light from your forehead. This is the light from your nose, and this is the light from your chin. It bounces off your face in a straight line towards the spoon, but the chin light is going to keep going this way. Your forehead light's going to go this way, and your nose light, I should cross in the middle there, and your nose light is going to come back in where it was. What's that going to do when you actually perceive the image? You're going to see your chin up here, your nose in the middle, and your forehead down here. Looking at the inside of it, looking at the back of a spoon stretches your image. Looking at the inside of the spoon does what? If you see your chin above your nose and your forehead below your nose, it inverts it. Yeah, it flips it upside down. So this could be and now look, you have my spoon, observe your face. If you really never did that as a kid, the inside of the spoon inverts the image. And pass the spoon. Everyone, for the first time in your life, gaze at your reflection in a spoon. I believe you. Everyone denied it. Well, now you've done it again. Okay, so that's reflection. Reflection's an interesting phenomenon. Wave pulses are a little bit different. Wave pulses get interesting. Alina, you're going to help me demonstrate these. Here we go. Where's the two we're going to look at? Here's my giant slinky again. We're going to take this under here. Well, do you want me to take that in? No, I don't want to take the rope. For now, hold it where it's at, hold it on the spring. I'll get this all close. No, I'll go that way. I don't think it's necessary. With the reflection in this. Oh, you're good. I'm going to stretch this away. Okay, so that was reflection in off a surface. There's other ways things reflect though. So depending on the kind of experience your wave is having, you can reflect off different things as well. So this one I'm going to show you is an example of a wave reflecting off different interfaces. So Lena, I'm going to go down on the ground again. Yep. The first one, so Lena's got, you're holding the spring, right? Okay. That's the fixed end. So this is the demonstration of I'm going to send a single pulse down, and we're going to see what the reflection looks like bouncing off. So the fixed end. So I'm going to pull it this way. I've pulled it to my right, Lena's left. The pulse goes down. What happens? It goes down. What is the wave doing? What is the pulse doing? Does it go on the same side or does it flip? It flips. It looks the opposite. Again, all the time. A bit bigger. Okay. You all see the effect I'm going for here? Yeah. Lena, I want you to hold the end of the string this time. Let go of the string. I put it back a little bit. So this is an example of two different media. I've got the spring and now that light string. That one. It's coming in the same way it's going up. Can you grab this one once? Can you grab the spring again? If you grab just this, hold it right to the back of the string. Pull back further. Give me a longer step. There we go. What's this one doing? This is what the effect I was looking for. So in one it flips. What's it doing on this one? Is it flipping as it bounces off that middle piece? No, it's coming back on the same side. So it depends on how that wave interacts, or what kind of end, what kind of barrier the wave interacts with. If it's that fixed end like it had before, the wave actually flips. Moves around to the other side of the needle. When it hits that knot, so you were holding it back far enough the first time. When it hits that knot, that's an example of an interface between two different media. Waves will actually reflect off that, as you can see. It's bouncing off of that and it's coming back on the same side. Yeah. So we're going to draw what we just saw. For a wave coming in, for a reflected wave pulse coming in and hitting like with a hard end, the direction of the wave pulse was in and it was up. On the way back, the direction was that way, but it flipped when there was a fixed end. And on this one, it stayed on the same side. I'll draw it like that. So this is an example of a barrier, a firm barrier. This is an example of the change in medium. When a wave hits a change in medium, some of it went through, like the string did move a little bit, but the pulse itself, a large part of it, bounced back off of the barrier, the change in medium, but didn't flip. It came back the same way it went in, which is an interesting effect. So when a wave pulse is reflected from a fixed end of a spring, the pulse returns on the opposite side of the spring. This would be true too if for any sort of transverse wave. So light would be an example of this. But when a wave pulse is reflected from a free moving end of a spring, the pulse returns on the same side. When you're ready, flip the page. So when waves bounce, you get an interesting effect. Because if we had, so like at the wave pool, or with sound, you never have a single pulse. You have something that's pumping. It's generating wave after wave after wave, and so you get successive waves coming at you. Sound is the same idea. It's for something that's constantly generating a sound, you're getting that same wave continuously coming at you. It's not a single burst, it's a whole blast of sound. And so when you have sound that starts to bounce off, or waves rather, that start to bounce off other surfaces, you start to experience those waves differently. And those waves are going to start interacting with each other. When they do that, we say that they interfere with each other. So there is an interference that shows up when waves interact. So one characteristic that makes particles different from waves is that in the case of a head-on collision, a particle is going to rebound. You've experienced this. We looked at momentum. When I had one object, like on a pool table, if you have one ball sitting there and you throw another ball at it, they'll interact with each other, they'll hit each other, and then bounce off in separate directions. Momentum, we've looked at it already. But waves don't. Waves pass through each other. The energy is allowed to interact, but the energy of each wave is going to keep going in the direction it was traveling in. It's a different effect. During the collision of the two waves, they interfere with each other in what we call an interference pattern, but the wave is allowed to continue, each section of wave is allowed to continue moving in the direction it was originally moving in. So in this case, it produces what we call an interference pattern, and the interference pattern has a different amplitude than either of the two original waves. And the calculation for this is really easy. All it is, as you're looking at these things, you want to add and subtract, add or subtract the amplitudes of the two original waves. And you get some interesting effects here. Anything that is a wave behaves this way and will interfere with each other. So if I've got two different waves coming in, I know I've photocopied this so they don't look blue and green. But if I take a look at what's going on here, this wave here, this first wave, is coming in and it's moving to the right, and here it's at equilibrium. At this point, it has an amplitude of 4. Here it's at equilibrium again. Here it has an amplitude of -4, and here it has an amplitude of 0 again. It's at equilibrium. If the blue wave is moving to the right and the green wave is moving to the left, the green wave is weird. This one is at equilibrium, up to equilibrium, up to again. It's not inverted at all. It's one pulse up, and then back at equilibrium. You can see here that if you overlap them, when these waves are maximally interfering with each other, that means they're fully on top of each other, you get this effect where the amplitude of the first bump, they're in the same direction. So this one had an amplitude of 4, this one had an amplitude of 2. So when the waves are stacked on top of each other, they actually produce one larger wave that has an amplitude of 6. And whereas we call this is an example of what we call constructive interference, where the two waves are allowed to build on each other. And if we look over here, this one had an amplitude of -4, this one had an amplitude of +2. So these two amplitudes are in opposite directions, and so what you get here is that these two waves start to cancel each other out. So this one was +2, this one was -4. What they do when they overlap is they create a wave that has an amplitude of the big one minus the small one. So you get destructive interference here, destructive interference, where the wave pulse, while they're overlapped, is smaller. So the math here looks like this. The first dot was 0 plus 0 is 0. The second dot, this guy here and this guy here, 4 plus 2 gave us an amplitude of 6. The third dot was on both was 0 and 0 again. The fourth dot was at -4 and +2. So that gave us an amplitude on the interference pattern of -2. And then the fifth dot was at 0 again. So the final was at 0. I could demonstrate an example of this too. Why is my pen small like that? Okay, Nina, you're up again. So you actually need to make something happen this time. Well, hold this string, hold the spring. Let's see if we can do this. Okay, so I want you to grab the spring rather, like I'm doing. Yeah, and you're going to send a pulse on the same side that I'm sending a pulse. So my wave's going to move towards you, your wave's going to move towards me. In the middle, these things should, because they're on the same side of the spring, they should build. So let's see what we see. So 1, 2, 3, go. Okay, I'll count to 3 and then I'll take it. 1, 2, 3, go. Right. Oh, we don't see the effect. 1, 2, 3, go. You can see that they're moving past each other. Let's see if we can go the other way. Let's see if we can create a destructive interference pattern. 1, 2, 3, go. It looks like in the middle there's a point where it's dead. Do it again. Here, let's do it again. 1, 2, 3, go. You're going to section the middle of the spring where it looks like nothing's happening. When they overlap each other at that point, they're destructively interfering. The spring looks like it's moving. So we can make some interesting interference patterns. Or interesting wave patterns. How you'd actually do this, I have no idea. But let's say we've got a blue wave traveling to the right, and it looks like this pattern. It's got, at the first dot it's 0, second dot it's 2. Here we're at -3, here we're at -2, and 0 in the middle here and here. And you send a green wave going to the left. You've got the first dot is an amplitude of 2, the second dot's a -2, the third dot's a +2, the fourth dot is a 6. Again, how you generate this kind of pulse, I don't know, it doesn't matter. Assuming we're able to, when these two waves cross each other, you're going to get a pattern that looks like what? Well, we just lay the two waves over top of each other and we do some math. Let's put the dots where they should be. And we'll take a look at what the interference pattern would be for these two waves. When the first two dots overlap each other, or the first dot on the two different waves overlap each other, one has an amplitude of 0, and the other one has an amplitude of 2. So their combined wave is going to have an amplitude of what? 0 plus 2 is 2. At the second set of dots, one has an amplitude of 2, the other one has an amplitude of negative 2. So what should these two do? 2 plus negative 2 is going to cancel out, give you 0. This one's going to be at 2. This one's going to be at negative 3. So 2 plus negative 3 is negative 1. And in the last wave interaction, you're going to have one is up at 6 and the other one's down at negative 2. So 6 plus negative 2 equals 4. And now we can actually go ahead, plot these dots, and draw out what the interference pattern is going to look like. So at the beginning, 0 plus 0 is 0. 2 squares in, 0 plus 2 is 2. Here we're going to be back at 0. 2 more dots, we're going to be back at 0. Over 2 more dots, we're still going to be at 0. Over 2 more dots, we're still going to be at 0. Over 2 more dots, we're going to be down at negative 1. Over 2 more dots, we're here again, so back at 0. And then over 2 more dots, it's going to be this one and this one are going to interfere and put us back at 4. And then at the end, they cross each other at 0 again. So that's the dot pattern. We can go ahead and we can connect these lines. It's going to look something like this. You're going to get an interference pattern that looks like that. Comments, questions, concerns? Okay, I'll flip the page. Okay, cool. So this is called, yes. What about it? Yeah, Greg had the same problem too. He just made some noises, so I don't know what that was about. Are you connected to the Wi-Fi? Because the Wi-Fi was giving me some grief earlier. Here, let's test this. I'll do a test print. Sorry, guys. Bear with me. I came in on Tuesday night and printed just fine. Let's see what happens. So the only difference between you and I is I'm hardwired in and you're not. Okay, so the idea that these waves are going to interfere with each other is called the principle of superposition. I'll do a couple examples of this and then leave you to play with this, I think is where we're going to end it here today. Do I want to do that? Yeah. Sorry? Oh, is that what that is? Is that what it came out as? I do not need the test print. So we've got two waves that are approaching each other. At time equals 0, this is what they look like. You've got a wave traveling to the right at 1 meter per second. You've got another wave traveling to the left at 1 meter per second. So what's this? And then let's assume every square, well, actually we're told from here to here is 4 centimeters. So each of these represents 1 centimeter. This is going to be weird. This should actually be in centimeters per second. Yeah, this should be in cm per second. So if the wave is traveling at 1 centimeter per second and this one's traveling at 1 centimeter per second, what's happening as this time is progressing? After 5 seconds, this edge is going to have moved 5 little squares. So it's going to be 1, 2, 3, 4, 5 is going to be that guy there. 1, 2, 3, 4, 5 is going to be that guy there. And so the pulse is going to look like this. This guy is going to be 1, 2, 3, 4, 5. He's going to be right there. This guy is 1, 2, 3, 4 away. So 1, 2, 3, 4 away. And you're going to have a wave that looks like this. So after 5 seconds, these two different waves are just about to interfere with each other. At the 7-second mark, which is 2 seconds later, it's going to be difficult for you to draw this if you don't have a different color. But I'm going to draw it like this. This piece, after 2 seconds, has moved 2 more forward. So it's going to be there. The back piece is going to be there. And so you're going to get this piece. I'm going to draw this other one in green, different green. This piece of wave will have moved 2 more squares. So it's going to be there. This one will have moved 2 more forward. So it's going to be there. And so you're going to get these 2 pulses, and you can see after drawing them, these 2 are laying over top of each other. And so what you're actually going to get here is a wave that looks like this. That edge is going to be at 0. If this one's at 1, 2, 3, and this one's at 1, 2, you're going to get a wave pulse that's up at 1, 2, 3, 4, 5 for as long as they're interfering with each other. So where these 2 pulses are overlapped, you're going to have something that looks like this. And then it's going to look like this. And so at the 5-second mark, you're going to get a pulse that looks like this. This black one that I've drawn over top. 2 more seconds later, I'm not going to draw this one, but we'll talk about it. 2 more seconds later, this pink one will have moved 2, and this green one will have moved 2 more. And so you're not going to get, they're not going to be overlapped at all. You're going to get this wave on its own to the left. This wave will be on its own to the right. And so you're going to have something that's kind of staircased, tiered down. But you can get the idea that as they're moving, they're going to start to interfere with each other. This is the principle of superposition. Okay, here's what I'm going to get you to do. I want you to play with this a little bit. Flip the page. There's a few of these drawings I want to get you to do. And I've actually given you separate graph paper for this one. So what I want you to take a look at is examples of these kinds of drawings. These first 3 are all, they give you the waves traveling in. They don't give you time frames to work on. They just say, okay, I want you to draw what it looks like for the 2 waves to be half on top of each other. So overlapped half and in the top one, and completely on top of each other in the bottom one. So what will that look like in each case for this wave, and this wave? So I want you to do this, I want you to practice with this page. Flip the page. I want you to take a look at this one as well. This one will be similar to the example I just did. You've got 2 waves traveling in, and at different time periods, these 2 pulses are going to overlap with each other. What's that pattern going to look like? On the top one and on the bottom one. And that's all I'm going to get you to look at now. That's what I want you to play with. We'll look at the other ones. Yeah, we'll look at the other ones tomorrow. Do I want the other ones tomorrow? Or do I want to finish it off here now? How much time do I got left? You know what? Start there. We'll see what happens. Draw me these pictures. Take a look at this page and the next. On your market set giver, we'll see what that does for time.